Before we dive into the largest stars in the universe, let's begin with something more familiar: Earth. While Earth itself is insignificant in size compared to even the smallest stars, it serves as a useful reference for understanding scale. The largest planets in the universe, known as gas giants, are the closest non-stellar objects to stars in terms of mass and composition. In our solar system, the most prominent example is Jupiter. This immense planet is approximately 11 times the diameter of Earth and has a mass that is 317 times greater. However, despite its enormous size, Jupiter is still composed mostly of hydrogen and helium, the same elements that make up the Sun, yet it lacks the necessary mass and internal pressure to initiate nuclear fusion and become a true star. The transition from planets to stars occurs in objects known as brown dwarfs, which occupy a peculiar middle ground between gas giants and true stars. Brown dwarfs are often referred to as failed stars because they have a mass between 13 and 90 times that of Jupiter, which is enough to trigger limited nuclear reactions but not sustain full hydrogen fusion like a main sequence star. Interestingly, brown dwarfs do not significantly increase in size as they gain mass. Instead, the additional mass increases their density, causing their core pressure to rise. This heightened pressure allows some nuclear reactions to take place, causing the object to glow faintly. However, they never reach the critical threshold necessary to sustain hydrogen fusion, meaning they remain dim and relatively cool compared to actual stars. Brown dwarfs are more massive than Jupiter, but still fall short of becoming true stars. So, where does the transition occur? A celestial object officially becomes a star when its core reaches a high enough temperature and pressure to sustain hydrogen fusion. When hydrogen atoms fuse into helium, they release tremendous amounts of energy in the form of light and heat, allowing the star to shine. These stars, known as main sequence stars, form the backbone of stellar classification. The more massive a star is, the hotter and brighter it burns. However, mass comes at a cost. The more fuel a star consumes, the shorter its lifespan. At the lowest end of the main sequence are red dwarfs, the smallest true stars. These stars have around 100 times the mass of Jupiter, but only just manage to sustain fusion. Their low mass means they remain relatively cool and dim compared to larger stars. Red dwarfs are the most abundant stars in the universe, making up roughly 70% of all stars. Because they burn through their fuel so slowly, they can last for up to 10 trillion years, far longer than the universe has existed so far. One well-known example of a red dwarf is Barnard's star, located just 6 light years away from Earth. Despite being one of our closest stellar neighbors, Barnard's star is too faint to be seen without a telescope. As stars become more massive, their properties change dramatically. Our own Sun, a G-type main sequence star, is a prime example of a mid-sized star, accounting for 99.86% of the total mass of the solar system. The Sun shines brightly due to the immense energy produced by nuclear fusion in its core. It is 7 times more massive than Barnard's star, but emits 300 times more light, and has double the surface temperature. Even small increases in mass can significantly impact a star's brightness and lifespan. For instance, Sirius, the brightest star visible from Earth, is twice as massive as the Sun, but shines 25 times brighter. More massive stars, such as those in the Beta Centauri system, can have surface temperatures exceeding 25,000 degrees Celsius, and radiate tens of thousands of times more energy than the Sun. However, these massive stars burn through their fuel at an accelerated rate, often exhausting their hydrogen supply in just a few million years. The most massive star we know of, R13601, contains an astonishing 315 times the Sun's mass and radiates nearly 9 million times more light. However, despite its incredible brightness, it is only about 30 times the Sun's size. Its extreme radiation continuously strips away its outer layers, shedding an estimated 321 billion tons of material every second. Stars like R136A1 are incredibly rare because they approach the physical limits of star formation. When such a massive star forms, its intense radiation can prevent surrounding gas from accumulating, limiting further growth. The theoretical upper limit for a single star is thought to be around 150 times the Sun's mass. Any more than this, and the star risks blowing itself apart due to its immense energy output. If adding mass doesn't necessarily make a star larger, then how do we find the biggest ones? The answer lies in their evolution. As stars exhaust their hydrogen fuel, their cores contract, while their outer layers expand dramatically. Even relatively small stars can swell to massive proportions during this phase. For example, Ga Crux, which is only 30% more massive than the Sun, has expanded to 84 times its original radius. Hypergiants represent the most extreme case of stellar expansion. These stars have vast surface areas and emit enormous amounts of energy. However, their gravity struggles to contain their outer layers, which are continuously blown away by intense stellar winds. One such star is the Pistol Star, a blue hypergiant with 25 times the Sun's mass, but 300 times its radius. These massive stars have incredibly short lifespans, typically only lasting a few million years before undergoing supernova explosions. Even larger are yellow hypergiants, such as Rogue Cassiopeia. This star, visible to the naked eye despite being thousands of light years away, has a mass 40 times that of the Sun, a size 500 times larger, and a luminosity 500,000 times greater. If Earth were located as close to Rogue Cassiopeia as it is to the Sun, we would be engulfed within the star's outer layers. The current record holder for the largest known star is likely Stephenson 2-18. This incredible red hypergiant, which initially had only a few dozen times the Sun's mass, has since shed much of its material while expanding to an estimated 2,150 times the Sun's radius. To put this into perspective, if Stephenson 2-18 were placed in the center of our solar system, its outer layers would extend beyond the orbit of Saturn. Traveling at the speed of light, it would take 8.7 hours to complete one full orbit around it. By comparison, Earth's fastest aircraft would take over 500 years to accomplish the same feat. As Stephenson 2-18 continues evolving, it will likely shed even more mass before collapsing into a supernova. The remnants of its explosion will scatter across space, seeding the next generation of stars and planets, continuing the endless cycle of a cosmic evolution. The universe is home to objects of unimaginable size and scale, from small red dwarfs to the largest hypergiants. Understanding these stars not only helps us comprehend the vastness of space, but also provides insight into the processes that shape the cosmos. Thank you for watching.